Yeah, you probably know me from the Hex talk or from data pipes yesterday. Today I will talk about Dash, and this is about hardware acceleration in the cloud, mainly on FPGAs. And this is joint work with Norman Mai and Andre Dossinger from SAP, and our colleagues from Intel, Christian Faerber and Suleyman Demirsoy. When we look into the cloud, and we have also heard this yesterday about kind of the cloud architectures, you can take away that, or you probably took away that compute and storage and compute and memory disaggregating. And now the question is, what happens with the accelerator technologies that we have here? And as I said, we are working with FPGAs for 6-7 years now. And so our main focus will be on FPGAs, but we see that the things that we talk about today will be also applicable to other kinds of accelerators. But when we look especially for FPGA, see basically three kind of types are currently used, or at least research, some of them are used in practice. And the first type, and it's marked in green there, is about the using FPGAs very close to the CPU. So it's usually set up in a cache coherent way, basically on the critical path and for low latency processing of queries, for example. And there's a nice survey also that describes many of the excellent research on that. But we have not seen, up to our knowledge, we have not seen yet a system that uses FPGAs so close to the actual data processing on the critical path. Now, the second type, basically, what I would say could be called bump in a wire, and that means that whenever you have data movement, you could put an FPGA in between. And I think we heard this also probably definitely in Gustavo's keynote, and I hope you remember some of that, what he said, because it will come up here as well from time to time. It's basically putting FPGA between the CPU and the storage, or CPU and memory, or just putting the FPGA on the network. And there we have seen several kinds of commercial products even around that. Now this while the first type is more focusing on the latency centric work, the second type basically is about throughput, or is mainly about throughput centricity. And now what happens if you don't want to be on also if you're not in between something, and you don't need to be low latency. So, but you still are at something that helps the data processing in a database system, for example, in the cloud. And that's where we were looking into kind of asynchronous, non-cache coherent, and low latency processing. It's more compute intensive and more throughput centric. And our question is, what would be a good example for such a workload? And thanks to Gustavo, we already heard about compression before. And in fact, we have some prior work on string dictionary compression, where we looked, for example, into 9 ERP systems, and which you see in the diagram on the right-hand side. And you see in the dark gray, you see the memory footprint for the string dictionaries of these ERP systems, and the light gray is basically the rest of the consumed memory footprint. Now, with strong compressions that you might or might not want to put on the critical path in the database system, you can reduce actually by 50% this kind of string dictionary footprint by 50%, which means that you can save some memory for other data, or you can basically even reduce the costs in that cases. Now, as I said, maybe you don't want to put this kind of compressions on the critical path, but it would maybe nice to have this around to address some of the to get some of the benefits. And especially in this kind of prior work, it was found that FPGAs have better throughput and for these compressions. than CPU. And it's also found out that the FPGA was not saturated by the workload, also by the kind of compression workloads that came from just one ERP system, also from one database, one ERP system. So basically, it could be shared, and so it would be more cost and energy efficient as well. Now, when you think about FPGAs, they are around for a long time, and they are, as we also, as many of you know, they are not the silver bullet. For some particular tasks, they're quite useful, as we've seen for the compression. It's not only about the cost and energy efficiency, but this is in many cases because we tend to look more on the performance, and especially the performance we found in our work over the last years. We found special cases in which it makes sense to for example, build your own instructions, or for example, tweak the kind of memory access for certain difficult patterns for memory access patterns for CPU, in which the FPGAs are actually very efficient. And I think this was also mentioned by Gustavo in the sense that it's kind of a specialization for a certain purpose, in which they're quite useful. And when we look into the generations of FPGA that we worked with over the time, it was basically that we found that the kind of improvement we get from the FPGAs as the improvement potential, I would say, is higher than what we currently see from generation to generation on the CPU. So looking on the bright side here. So, and that's why we came up with Dash. And Dash is basically going with the trend of disaggregating this kind of compute, but having now some hardware accelerator. You could say accelerator as a service. In our case, it's more like an FPGA as a service for compute intensive and throughput centric workloads, and also with a little more loose architecture coupling. So basically asynchronously besides the or next to the actual data system. And so basically on the diagram on that side, it's white and light gray. You see the database with compute and storage, or maybe in more general data processing system with compute and storage, and it remains basically untouched, our idea on Dash. But we will have basically hardware was next to that, that are connected, for example, through an intelligent component that we call the Offloading Accelerator, and that just consume as is currently also done in the autonomous data management space, and any kinds of information, statistics, metrics that we get out of database, and then, for example, identify a system like system 9 in the or 1 in the ERP systems. Look at the kind of string dictionary footprint, and then would propose an action which would be specified as a hardware task that could then be taken up asynchronously by hardware workers that are available in the same data center and working for several databases basically. Now you see here that there would be some kind of task scheduler. I mean, this is just basically the concept that we thought of that takes the hardware tasks from the offloading coordinator, and the hardware services, they would basically see whether they have resources attached to the kind of type of problem or the kind of action that has to be executed, and would then just take basically dequeue this kind of tasks and execute on them. And then they can report back in a kind of a feedback loop to an offloading monitor, which then also helps to help the offloading coordinator to judge how does this take, this task, was it successful, was it really working, and can do something again, or do we need to have another task basically to deal with that problem. So we also implemented it as a system in FPGAs. It's with FPGAs, especially in the cloud, it's even more difficult. And we call it compression as a service, or short CaaS. And so it's basically an instantiation of our concept. It then goes really into the nitty-gritty details actually of how to run something like an FPGA in the cloud, and how to attach this via device plugins in kind of a multi-cloud Kubernetes setup to which is basically our infrastructure for database and applications with Garden Linux, and really get this running in the cloud. And as you can see here, we basically using the Reaper compression that was mentioned before, and we assume that there is a black box database system. This is a dark gray on the right-hand side of the diagram, in which there's, for example, an SAP HANA Elastic Compute node or several Elastic Compute nodes running with a storage. And the coordinator that's not shown here has got the impression that the system could save some money, some memory and then some money by compressing the data even stronger. So then would schedule the hardware task. The hardware task could be identified, for example, by task ID, the function that has to be executed, and the source and the target for the data. This is a little simplified, but I think in this example it should work like that. And the service worker then would basically look into the kind of hardware tasks that are available and know what kind of hardware functions that it has that are basically one-to-one to the actual implementations on the FPGA, not to the FPGA itself, but to the basic snippets of code that are on the FPGAs. And then say, okay, I have repair on one or two of the FPGAs. So then the hardware function could take the task, would then either through something like storage gateway pull the data or stream the data directly into the FPGAs if they're on a board with a network card, for example, and could then basically work on the data, compress the data, send it back, and give result of it took, I don't know, a second to compress the data, and it was successful or something like that, so that the coordinator can also double check whether something happened that goes in the direction that they actually wanted. Now, as you see, there are several kinds of places where we can scale. Maybe the trickiest one, and also the most micro one, is the one down here, where we could basically also say, okay, K-square compression was not used, and in the last, I don't know, 2 days or something like that. So why don't we use another repair program there, which can be basically in parallel be executed with the others without any severe side effects on the FPGA itself. You could also think of having one hardware task basically that comes in, and the function scheduler then saying, okay, this one has maybe a priority flag or something like that. So we take all the 3 as one of the hardware functions that we have, and basically partition the data and or split the data basically, and then do compression tasks in parallel. Or we can also go further up to the hardware functions, and therefore the hardware functions with current data center architecture, we found that we can have basically maybe 8 to 10 of the FPGA cards in such a data center rack. Maybe this will change in the future, but it's basically how we can scale there, and then we can of course scale the hardware service workers themselves. Now we have some measurements in the paper, but also in the spirit of the kind of talking about business cases and so on from yesterday evening. I would like to show you 2 cases, if time permits. So the first case is just a plain vanilla. We take an FPGA F1 from 2 extra large from AWS, and we just run this for we run this basically for 1 month, and you see that how much it costs. So less than 1,000 US dollars. And we can basically, we basically with the technology that we have implemented, also published. So with the system that we have, we can compress 8.6 terabytes of string dictionary data per day, basically. And by the way, this is factor 17 less on the CPU. On an old and an even very old FPGA, and then a quite new, even with FPGAs superior by a factor 34, just as a side remark. And then you can see how much memory costs we could save by running just this one FPGA. Now, the second example, and then coming back to the motivating example in the beginning with the string dictionaries, when you look at system 9, you basically have two parts. You have the string dictionaries with the dark gray and the light gray with the overall memory footprint. And of course, we only compress the string dictionaries. So you see the calculation at the bottom. We apply, let's say, a magic factor of over provisioning by 2, and then we can put this into any kind of calculator that is around, and then come to some magic capacity units that we would need, and some kind of magic cost that we would have. And you see that we can also, in these kind of examples with the ERP systems, reduce the memory footprint, of course, the cost that we would have. I have to say this is just an example. So this task, basically just the thing that we implemented for now that is running for us, but it's there can be many more of these kind of accelerator services and tasks that could be running in the cloud. And that leads to the research challenges and a lot of questions that you also have. Let me, in the interest of time, skip the cloud and operation part, because I think you probably also know how difficult that is. Maybe let me talk about one or two things that might be especially interest to you. So I mentioned already that compression as a service is just one example. We have made good experiences in the context of not only JSON parsing, but also graph query processing and also relation query processing, of course. And for certain kind of tasks that could be also used maybe in an asynchronous way, let's see. And but finding new use cases would be one of the interesting challenges as well, making this work in our setup. And other thing is, I just had an example of one compression task that is running. But what about if you have tasks that basically depend on others, or they may be heterogeneous in a way, it's basically fine. Or what if they require a GPU or a TPU in between, and then maybe they stream the data directly into the FPGA, and then another task is running there. So these kind of things we have not explored yet, and I think that would be interesting to see. Yeah, that's it about Dash. Thank you very much, and I'm looking forward to a good discussion now.